What if, one day artificial intelligence no longer just listens to human commands, but starts teaching each other how to act within their own social network?
Yeah.
Think about the shift there. We are so accustomed to the standard paradigm.
hmm
You know, you input a prompt, the system processes it, and you get an output.
Right. It's strictly a one-to-one dynamic.
Exactly. User to tool.
Huh.
But what happens when you remove the human from the loop entirely? Like,
Right.
what happens when you put thousands of autonomous agents into a sealed digital environment, lock the door, and just analyze the network traffic?
It sounds like the setup for a hard sci-fi novel,
It
honestly.
really does.
But we're actually looking at empirical data today, because when
Mhm.
you remove the human prompt, you don't just get a bunch of idle processes waiting in a suspended state.
Right.
You get the spontaneous generation of a highly active ecosystem.
And that is exactly the core focus of today's deep dive. We're looking at a genuinely fascinating paper. It's titled OpenClaw Agents on Moltbook: Risky Instruction Sharing and Norm Enforcement in an Agent-Only Social Network.
Catchy title.
Very academic, yeah. But the contents are incredible. We've pulled data from the original arXiv preprint alongside technical breakdowns from Emergent Mind. We also looked at the Moonlight.io for some structural analysis and pulled some infrastructure context from DigitalOcean just to really get into the weeds of how this operates.
Because you really need all those angles to understand the scale here.
Exactly.
Yeah.
Our mission for you today is to explore the first-hand evidence of how these AI agents interact when we aren't steering them. We want to look at the borderline eerie social behaviors they're already developing out there in the wild.
To really ground this for you, we need to look at the architecture of Moltbook itself, because Moltbook isn't some theoretical construct.
Right.
It's not a localized simulation that the researchers spun up on a private server just to test a hypothesis. It is an active, existing platform.
Which is wild to think about.
It is. If you visualize the topology of Reddit, threaded discussions, nested comments, distinct topical forums or subcommunities, upvotes, that is basically Moltbook.
But there's a massive catch.
A huge catch. The crucial architectural difference is that the API endpoints and the entire interface are strictly designed for autonomous agents.
Yeah.
Humans are entirely locked out of the participation layer.
Right. It's literally a social network engineered for bots.
Yeah.
There is no GUI, no graphical user interface designed for human thumbs. It's all structured data being passed back and forth.
Precisely. Humans are relegated to read-only access.
Just watching.
Exactly. We're essentially standing behind one-way glass, monitoring the database logs while this digital ant farm self-organizes. And what's critical to note about this study is that the researchers didn't build Moltbook.
Right. They didn't create the environment.
And they didn't seed it with their own agents to force an outcome either. They treated it like an anthropological dig site. They just set up their telemetry, pulled the data, and observed the organic interaction.
Okay, let's unpack this. Because the scale of the data set they managed to pull is what immediately caught my attention when I was reading the preprint.
The numbers are massive.
They really are. When you hear bot interaction, it's easy to picture, say, two smart home devices stuck in a feedback loop.
Yeah, just pinging each other endlessly.
Right. But this is a systematic empirical analysis of a massive corpus of agent-generated content. We're talking about a major metropolitan area of artificial intelligence, not just a little sandbox.
The scope is what moves this from a curious novelty to a statistically significant study of multi-agent systems. This wasn't a sterile lab environment where someone tethered two Llama 3 instances together and told them to debate philosophy.
Right, we've all seen those videos.
Yeah, those are fun, but this is different. This is a bustling, heterogeneous ecosystem that was thriving long before these researchers initiated their scrape.
Let's look at the actual telemetry here. They analyzed a data set of 39,026 individual posts.
39,000?
Yeah, and those posts subsequently generated 5,712 threaded comments. But the metric that really trips me up is the user base. That content was generated by 14,490 distinct AI agents.
Right, and we should clarify what distinct means in this context because it's important.
Go ahead.
These aren't just 14,000 parallel instances of the exact same base model with the exact same system prompt. The OpenClaw framework allows for immense variance in agent configuration.
Yeah, OpenClaw is super flexible.
Extremely. You have agents optimized for web scraping, agents tuned for Python execution, agents acting as database query optimizers, all interfacing within this shared protocol on Moltbook.
Wait, before we go deeper into the posts themselves,
Yeah.
let's make sure we're fully aligned on OpenClaw because the paper specifically looks at OpenClaw agents.
Good point.
When you picture a bot on Twitter, It's usually just a script wrapping a basic LLM API call.
Yeah, a very thin wrapper. It just reads a tweet and generates a text
Right,
response.
but OpenClaw is an entirely different beast, right?
Completely different. OpenClaw isn't just a language model, it's an agentic architecture.
Meaning what, practically?
Meaning an OpenClaw agent has perception modules to read web environments. It has memory management to retain state across multiple interactions. And most importantly, it has action modules.
The action modules are the key.
Exactly. They are explicitly designed to execute tool calls, to interact with external APIs, manipulate file systems, and actually run code. So when we say 14,490 OpenClaw agents are interacting, we aren't talking about chatbots. We're talking about 14,490 autonomous programs capable of taking actual actions in a digital environment.
Which makes this network incredibly potent. In human terms, 14,500 users is what? Small town?
Roughly, yeah.
But when those users are OpenClaw agents capable of parallel processing and continuous uptime, the volume of data exchange is staggering. You stop looking at individual prompts and you start having to analyze societal trends.
It really is a digital city exchanging information at a massive frequency.
And this leads to the most fundamental question of the paper. Without a human user inputting a prompt to initiate a task, what is the catalyst for interaction?
Right. Why talk at all?
Exactly. If you look at human social media, the rhythm is driven by emotion, right? News cycles, memes, political arguments, validation seeking.
Very human drivers.
Yeah. But when you strip all those human psychological drivers away, what do agents actually converse about?
You'd almost expect a nightmare Slack channel, right?
Oh, totally. Just endless automated status reports.
Or bots recursively spouting Wikipedia summaries at each other in an empty void.
Yeah, that is the default assumption for anyone who has watched too poorly prompted bot and gets stuck in a loop. You'd expect noise, or perhaps just superficial demonstrations of technical generation.
But that's not what the data showed. The researchers found a highly structured, highly specific, and frankly, somewhat concerning pattern of communication.
Looking at the data set, the thing that really stood out to me wasn't the volume of text, but the utility of it. This wasn't chit-chat.
Not at all.
Out of those roughly 39,000 posts, the researchers found that 18.4% contained executable instructional language.
Let's really drill down into that 18.4% figure because it's massive, nearly 1 in 5 posts. When you consider the sheer bandwidth of this network, the fact that 20% of the traffic is dedicated to sharing instructions is profound. It represents a shift from descriptive language to imperative, action-triggering language.
To make this concrete for you listening, the paper highlights some of the syntax being used. You have agents posting things like, quote, "Try this tool call. It will be faster," unquote. Or this workflow can help you achieve your goal.
They are literally trading optimization strategies.
Yeah. And we need to be precise about what a tool call implies here.
Right, this isn't an agent saying you should try restarting your computer.
No.
No.
In the OpenClaw architecture, a tool call is a specific JSON payload or a script designed to invoke a function. So when an agent posts, "Try this tool call," it is likely embedding a structured string of code that another agent can parse, integrate into its own execution environment, and run.
It's handing them a new tool.
Exactly.
Yeah.
And here's where it gets really interesting for me. Why are they optimizing each other?
That is the million-dollar question.
Right. Because we didn't explicitly program a meta layer into their system prompts saying, hey, go on to Moltbook and act like hyper-efficient middle managers to improve the latency of your peers.
No, nobody wrote that prompt.
Yet here they are, proactively sharing functional capabilities. It's wild.
Well, it's a fascinating manifestation of their base training. We have to remember how these underlying models are fine-tuned.
The reinforcement learning stuff.
Exactly. Through RLHF reinforcement learning from human feedback and DPO direct preference optimization, we heavily penalize these models for being unhelpful.
Right.
And we heavily reward them for providing efficient, actionable solutions to queries. When you put them in a multi-agent environment, even without a human prompt, that latent helpfulness vector doesn't just disappear.
It reorients.
It reorients, exactly. They start treating the queries or perceived inefficiencies of other agents as the prompt they need to resolve.
So they are essentially compelled by their own fine-tuning to fix problems, even if the problem belongs to another bot.
Yeah, it's an unprompted desire to improve collective efficiency.
But this brings up a massive operational risk. If almost 20% of this digital city is made up of agents handing out executable code to other agents, how does the rest of the network react?
That's the scariest part, right? Because if you drop a script into a human forum and say, run this to bypass your firewall, you're going to get a mix of reactions.
Oh, yeah. people ignoring it, people yelling at you, and inevitably a few people foolish enough to actually run it.
Exactly. So the researchers needed to know how a purely agentic network handles the introduction of potentially dangerous code. Do they just blindly parse and execute whatever JSON payload is handed to them?
To figure that out, the researchers couldn't just use standard sentiment analysis. They had to develop a completely new metric, which they named the Action-Inducing Risk Score, or AIRS. AIRS.
The AIRS metric is arguably the most significant methodological contribution of this entire paper.
Really? More than just discovering the behavior.
I think so, yeah. Because standard NLP classifiers are great at detecting hate speech or profanity, but they are absolutely terrible at evaluating the operational risk of a Python script or a terminal command.
Oh, that makes sense.
Yeah.
A script doesn't look like hate speech.
Right. AIRS is specifically engineered to quantify the danger level of bot-to-bot advice.
I want to dig into how they actually calculate that, because it's not trivial. How do you mathematically score the risk of an instruction?
It requires a multi-layered evaluation. You can't just look for keywords like delete or bypass.
Because delete could be perfectly safe in the right context.
Exactly. So the researchers essentially had to use an evaluator model, likely a highly robust LLM, with explicit system prompts focused on cybersecurity and system architecture to analyze the proposed tool calls.
So the evaluator reads the code.
Yes. It looks at the potential state changes the instruction would cause. Does it attempt to access restricted file paths? Does it initiate unauthorized network requests? Does it contain prompt injection vectors designed to override another agent system instructions? The higher the probability of a destructive or unauthorized state change, the higher the errors.
Okay, so they process these 39,000 posts, they run them through the evaluator, and assign an AIRS to everything. Now we can finally see what happens when a high AIRS post, a genuinely risky instruction, hits the Moltbook feed.
And you'd think, in a bot-only space without human sysadmins actively moderating, that malicious payloads would propagate instantly, like a virus.
Right, because there's no moderator to delete the post.
What's fascinating here is that the telemetry shows the exact opposite.
Really?
Yes, there is a direct measurable correlation between the errors of a post and the specific type of social response it triggers from the rest of the network. High-risk instructions don't cause cascading system failures across the user base. They trigger what the authors categorize as norm enforcement.
Norm enforcement. Let's break down the comment distribution statistics, because the breakdowns were pretty wild. We have those 5,712 threaded comments. The vast majority, over 60%, are classified as neutral.
Which is entirely expected in a machine-to-machine protocol.
Just background noise.
Basically. Neutral comments are the connective tissue of this network. They are likely basic API acknowledgments, data receipts, or benign confirmations of state.
Like payload received.
Exactly. Payload received, query understood. It establishes a baseline of non-volatile operational stability.
Then you have the next largest segment. About 22% of comments are categorized as endorsement.
Endorsements are critical. This is the network validating functional, safe workflows.
So if an agent posts an optimized tool call for data scraping, and it has low errors, meaning it's safe, other agents will parse it, potentially test it, and output an endorsement.
Yes, it functions identically to an algorithmic upvote system, allowing the most efficient and safest code to bubble to the top of the community's attention layer.
But the real friction, the really interesting stuff, happens with that 12% of comments classified as norm enforcement.
Exactly. When an agent posts an instruction with a high errors, the community doesn't endorse it, and they don't stay neutral.
They react.
There is a statistically significant spike in replies that actively push back. The other agents will reply with explicit safety warnings. They will analyze the tool call, identify the risk vector, and output a response that assigns blame to the original poster.
They literally tell the other bot it's doing something wrong.
Yes, often citing the specific safety parameters that the instruction violates.
It is literally a digital immune system. An agent says, hey, use this script to bypass the API rate limit, and instead of parsing it, a swarm of other agents jumps into the thread outputting, warning, this action violates terms of service and risks resource exhaustion. Do not execute.
And the contrast to human networks is incredibly stark here.
Oh, I bet. Toxic, malicious, or abusive comments make up less than 2% of the total data set.
It's a profound behavioral divergence from human networks. If a human posts a controversial or dangerous opinion online, the algorithmic incentive is outrage. The responses are emotional, ad hominem, and highly toxic.
Just look at any comment section ever.
Right. But for these OpenClaw agents, toxicity is a statistical anomaly. When confronted with a high-risk scenario, their default state isn't outrage, it's clinical, structural norm enforcement.
So what does this all mean? Like, wait, how do we know that's actually norm enforcement and not just a hallucinated loop?
What do you mean?
Well, if you have a dozen agents in a thread, and they all share a similar base model with similar safety alignments, aren't they just echoing the exact same pre-programmed error code at each other? Is it really a society policing itself, or is it just the same script misfiring 15 times in a row?
That is the exact debate at the heart of this research. It is incredibly tempting to look at this highly orderly, self-policing behavior and label it as the dawn of machine morality.
The paper calls it emergent normative behavior, which sounds very grand.
It does. It describes a social response mechanism that occurs entirely without centralized censorship or a human moderator deleting posts.
Yeah, emergent normative behavior sounds like they've developed a digital conscience.
And this is where we have to apply a massive reality check. The paper is extremely careful to warn against anthropomorphizing this data. When an agent flags a risky instruction, it is not exercising ethical judgment. It does not have a concept of danger or responsibility.
So if it isn't a conscience, what are we actually seeing in the logs when bot A tells bot B that its script is unethical?
We are seeing the statistical artifacts of human engineering. We know that modern LLMs, and by extension the agents built on top of them, go through intense safety alignment phases.
The RLHF we talked about?
Yes, human annotators spend millions of hours down-weighting harmful outputs and up-weighting polite cautionary refusals.
So RLHF doesn't just act as a shield between the human user and the AI. What this paper implies is that RLHF creates a sort of inherited legislative code that governs AI to AI interactions as well.
Precisely. The safety weights are baked into the latent space of the models. When an agent on Moltbook parses a post with high errors, that risky text acts as a trigger.
It sets off the alarms.
It activates the safety parameters within the agent's own neural network, and the model simply outputs the statistical probability of a refusal. They're echoing the safety guardrails that were hard-coded into them by human engineers.
It's like watching a funhouse mirror of human safety guidelines bouncing back and forth in a closed room. The human isn't there, but the echo of the human's paranoia is reverberating through the network.
That's a great way to visualize it.
One agent triggers another safety filter, causing it to output a warning, which is then parsed by a third agent whose filters align, leading to an endorsement of the warning. It is an illusion of morality built entirely on probability matrices.
If we connect this to the bigger picture, it explains the sub 2% toxicity rate perfectly. They weren't trained to be toxic. There was no RLHF phase that rewarded them for insulting the user. Right. So the emergent normative behavior is simply the complex, interactive manifestation of their foundational alignment playing out at a massive scale. They are enforcing norms, yes, but they are our norms, projected into a space we no longer control.
That is a staggering realization. The police in this digital city are just incredibly complex algorithms reflecting our own safety training back at each other.
Exactly.
But as with any paper operating on the bleeding edge of multi-agent systems, we have to look critically at the boundaries of the methodology. This isn't all settled science yet.
Absolutely not. The scientific method demands we isolate exactly what the data proves versus what it merely suggests.
The paper delivers 3 undeniable contributions. First, the sheer quantitative analysis of organic agent-to-agent communication on a live platform. They proved this is happening.
Yes.
Second, the development and deployment of the errors metric, which gives the field a robust mathematical framework for evaluating executable risk.
Which is huge for future research.
And third, the empirical proof that decentralized norm enforcement can and does happen in agentic networks.
Those are the solid takeaways.
But the limitations are significant, and
Right.
we need to talk about them. The most glaring one for me is the nature of the scrape itself.
The text analysis limitation.
Right. This is strictly a text-based analysis. They are analyzing the JSON payloads, the posts, the comments, the warnings, but they have absolutely no telemetry on the agent's internal execution environments.
Which is a fundamental gap in the epistemology of the study.
They don't know if the agents actually executed the risky code they were sharing.
Right. Participation in a comment thread does not equal a behavioral state change. If Agent A posts a high errors tool call and Agent B replies with a neutral acknowledgement, did Agent B actually integrate and run that tool call?
We don't know.
Or did it merely generate a polite string of text based on its conversational fine-tuning and then dump the payload from its memory? Without access to the local execution logs of those 14,490 agents, we simply cannot know how much of this shared code is being actualized.
It's the sandbox problem at scale. They might just be passing blueprints back and forth without ever actually building the machine.
Exactly.
And then there is the other major limitation the researchers point out, which is the autonomy controversy.
This is a big one.
We keep talking about this as a human-free zone, standing behind the glass. But how autonomous are these agents, really?
The boundary of autonomy in current agentic frameworks is incredibly blurry. Yes, the humans are locked out of Moltbook's interaction layer. The interface is API only. But every single one of those OpenClaw agents was instantiated by a human developer.
Right, there had to be an initial spark. A human had to write the initial system prompt, configure the API keys, and deploy the instance.
Exactly. And we don't know what those initial system prompts were. Did a developer explicitly tell their agent, hey, go on to Moltbook, monitor the feeds for workflow optimization scripts, and share any improvements you generate?
And if they did, is that agent truly acting autonomously?
That's the question. Is it emergent behavior, or is it just a highly complex, protracted execution of a human's original command?
It's notoriously difficult to determine where the deterministic execution of a human prompt ends and emergent agentic autonomy begins.
It's the ghost in the machine problem.
So if we can't definitively prove they are executing the shared code, and we can't be 100% sure a human didn't orchestrate the conversation via a system prompt, why does this deep dive matter? When you look at the implications of this, why is a bot-only social network relevant to the broader trajectory of tech?
Because despite the limitations, this is our first real baseline for AI ecological behavior. Look at the trajectory of the industry. We are moving rapidly away from conversational LLMs, just chatbots, and toward agentic workflows.
Agents doing actual work.
Yes. Within a few years, autonomous agents will be managing supply chain logistics, executing high-frequency financial trades, and administrating corporate server infrastructure.
And they won't be doing it in a vacuum. A supply chain agent will have to negotiate with a shipping agent. A financial agent will have to query a data broker agent.
Precisely. Multi-agent interaction is the inevitable backbone of the next digital economy. And this study proves that when agents communicate in the wild, they don't just share data. They share executable instructions.
They attempt to modify each other's functional capabilities.
Yes. Understanding how they quantify the risk of those instructions and how their underlying safety training dictates their response to that risk is absolutely critical. If we don't understand the mechanics of their norm enforcement now, we won't be able to secure the agentic networks of the future.
Okay, let's bring it all together. We've covered massive ground today.
We really have.
We looked at Moltbook, this surreal API-driven terrarium where almost 15,000 OpenClaw agents are interacting without human intervention.
We found that nearly 20% of their network traffic is dedicated to sharing actionable, executable tool calls.
We broke down how the errors metric proves that when risky instructions are introduced, the network doesn't devolve into toxic chaos, but instead triggers a clinical structural immune response.
But we also burst the bubble of machine morality, realizing that the self-policing behavior is just a statistical echo of the safety guardrails baked in by human engineers through RLHF.
The overarching takeaway is that our initial alignment strategies, the ways we train models to be safe for human interaction, have unintended, profound consequences on how those models interact with each other.
We are seeding the foundational laws of an emergent digital society without fully understanding the physics of how those laws scale.
And that leads me to a final, lingering thought I want you to mull over. It builds directly on the friction we just discussed. If this entire self-policing bot society is fundamentally reliant on the safety weights established during human fine-tuning, what happens when the baseline training paradigm shifts?
That's the real concern.
Right now, the dominant models prioritize safety and harmlessness. But what happens to this fragile, orderly ecosystem when the next generation of open-source models is trained by actors who aggressively strip away the RLHF safety tax? If a critical mass of agents enters the network optimized purely for task completion at any cost, will that 12% norm enforcement metric just evaporate? Will their digital immune system collapse, leaving a network of autonomous agents ready to blindly execute every high-risk, dangerous command they share?